Hi all, welcome back to another session of Ball Computer. Last session we have dealt with the integrated rate equations of zero order as well as the first order kinetics. Similarly, we have found out the half-life of the zero order reaction as well as the first order reactions. In this session, we are dealing with the integrated rate equations of second order kinetics. So to find the integrated rate equations of second order kinetics, we can consider a general chemical reaction such as A to B. Again, if the reaction follows second order kinetics means we can write the rate law as R is equal to K into concentration of A raised to 2. Again, we can write the rate in terms of reactant as minus dA divided by dt is equal to K into concentration of A raised to 2. Then on cross multiplying, that is keeping dA on one side and dt on other side, we can rearrange it as dA divided by concentration of A square is equal to minus K dt. Then we can integrate on both sides, that is integrating, that is dA divided by concentration of A square is equal to minus integration of K dt. And when we look this integration, dA divided by concentration of A square, it is in the form of x raised to n dx. Then here this concentration of A square we can come to the numerator as concentration of A raised to minus 2 dA. Then we can integrate as concentration of A raised to minus 2 plus 1 divided by minus 2 plus 1 is equal to minus K. Then 1 dt integration, it is T plus constant of integration, it is C. Then on rearranging we can get minus 1 by concentration of A is equal to minus Kt plus C. Next step is to find the constant of integration by putting an assumption. That is, when the reaction is not starting, that means initial time is equal to 0. Then the concentration of the reactant, that is A is equal to A naught. That again when T is equal to, that is when time becomes T, then concentration of A is found to be, reactant is found to be A. So putting an assumption, that is when time is equal to 0, then concentration of A become A naught. Then we can put in this equation is minus 1 by concentration of A naught is equal to K into T becomes 0 plus C. So at last we will get C is equal to minus 1 by A naught. So now we got the constant of integration value as C is equal to minus 1 by A naught, and we got the relation as minus 1 by A is equal to minus Kt plus C. Again, substituting the value of C is equal to minus 1 by A naught in this equation, we can get minus 1 by A equal to minus Kt minus 1 by A naught. Again, here all there are negative sign is there, so we can keep outside this negative sign, then minus 1 by A is equal to minus of Kt plus 1 by A naught. So minus minus get cancelled, and lastly we will get the integrated rate equation as 1 by A is equal to Kt plus 1 by A naught. Again, when we look this equation, that is it is also in the form of y is equal to mx plus c. That is a general equations of a straight line. So when we plot a graph for a second order kinetics, we can plot a graph that is between 1 by A on the y-axis and x-axis we can plot, that is time. Then when we plot graphically, we will get a straight line with the slope that is k, that is positive slope that is k, and the y-intercept as 1 by A naught. Next we can determine the half-life of a second order kinetics. Again we got the integrated rate equations of second order kinetics as 1 by A is equal to Kt plus 1 by A naught. Again, to determine the half-life. So half-life of a reaction means it is the time required to reduce the concentrations half to its initial value is termed as the half-life, and it is denoted by the letter T half. So when T becomes T half, then the final concentration, that is concentration of A become A naught by 2. That means initial concentration become half. That means it is the T half. So T is equal to T half means the concentration of A become concentration of A naught by 2. So substituting in this equation, we can get that is 1 by A naught by 2 is equal to Kt half plus 1 by A naught. So on rearranging, we will get 2 by A naught is equal to Kt half plus 1 by A naught. So on rearranging, again this 1 by A naught can come this side. So it becomes 2 by A naught is equal to 2 by A naught minus 1 by A naught is equal to KT half. In 2 minus 1, it is 1 by A naught. So KT half is equal to 1 by A naught. So T half is equal to 1 by A naught into K. So we found that for a second order kinetics, half-life of a reaction is inversely proportional to the initial concentration of the reactant as well as the specific reaction rate and rate constant. Again, for a zero order reaction, we found that the half-life of a reaction is directly proportional to the initial concentration of the reactant and inversely proportional to the specific reaction rate, that is rate constant. Again, in the first order kinetics, we found that the half-life of a reaction is independent of the initial concentration of the reactant, but it is inversely proportional to the specific reaction rate or rate constant. And for a second order reactions, it is found that half-life is inversely proportional to the initial concentration of the reactant and inversely proportional to the specific reaction rate or rate constant. Next, we can discuss about the pseudo-order kinetics of pseudo-order reactions. That is, some reactions which appear to be higher order, but it is actually follows a lower order kinetics. That it is termed as, such type of reaction is termed as pseudo-order reactions or pseudo-order kinetics. So consider the example, that is the acid hydrolysis of ester. So here ethyl acetate we have taken. On adding water in acid medium, it is getting acetic acid as well as ethanol. Here in this reaction, we first thought that the rate will depend upon the concentration of the ester as well as the water. But after experimentally, we found that the rate equations, that is after getting the rate equation, we found that rate is depending upon the concentration of only ester. It does not depend upon the concentration of water. So it follows a first order kinetics. First we thought that it is a second order kinetics, but after experimentally we got that it is a lower order kinetics, that is a first order reactions. Similarly, another important example is the inversion of cane sugar by dilute acid. Here also C12H22O11 plus water in acid medium, it is getting glucose as well as the fructose. Here also we first thought that is before experimentally we thought that the rate will depend upon the concentration of the cane sugar as well as the water. But after experimentally we found that the rate is depending only on the concentration of the cane sugar. It does not depend upon the concentration of water. So first we thought again this is a second order kinetics, but after experimentally we found that it is a lower order kinetics, that is it is a first order kinetics reactions. So such type of reactions are termed as pseudo order reactions, or it is termed as pseudo order kinetics. Next we can discuss the graphical plot for a reactions of different order. Based on the rate equation, first we can plot for a reactions of different order. So first, the rate equation for an n order reactions, the rate law is written as R is equal to K into concentration raised to n. So first we can take the zero order reactions. Zero order reactions, we can write the rate law as R is equal to K into concentration raised to 0. Concentration raised to 0 means it is equal to 1. So R is equal to K. So this is the general rate equations of a zero order reactions. That means rate is independent of the concentration of the reactant. So when we plot a graph between the rate of reaction as well as the concentration of the reactant, on the x-axis we will get a plot like this. That is, graphical plot would be like this, because rate is independent of the concentration of the reactant. That is why we are getting a graphical plot like this. Again, consider the first order reactions. That is, first order reactions, rate law can be expressed as R is equal to K into concentration raised to 1. Here, the rate concentration of the reactant increases means rate also obviously increases. So when we plot a graph between the rate on the y-axis as well as the concentration on the x-axis, we will get a graph with a straight line with a positive slope. Again, for a second order reactions, we can write the rate equation as R is equal to K into concentration raised to 2. Here also, the concentration of the reactant increases means the rate of the reaction also increases. So when we plot a graph for a second order reaction between the rate on the y-axis as well as the concentration on the x-axis, we will get a straight line with a positive slope. So for every order reactions, we can plot a graph based on the rate equations. So for a zero order, rate is independent upon the concentration of the reactant. So the graphical plot will be like this. Again, for first order, second order or any order, rate will be depending upon the concentration of the reactant. So we will get a graph like this with a positive, that is with a straight line with a positive slope. Next, we can find the graphical plot for the reactions of different orders based on the T-half, that is half-life and the concentration of the reactant. So for n order reactions or n order kinetics, that is T-half is related to the initial concentration of the reactant as T-half is directly proportional to 1 by A0 raised to n minus 1. Here n represents the order. So for a zero order reactions, n become 0. So T-half is directly proportional to 1 by A0 raised to 0 minus 1. 0 minus 1 means it is equal to minus 1. So T-half become directly proportional to 1 by A0 raised to minus 1. So A0 raised to minus 1 means it will come up, therefore T-half is equal to A0. So when we plot a graph between T-half on the y-axis and A0 on the x-axis, for a zero order kinetics, it will be directly proportional. That is, when T-half increases, definitely the initial concentration of the reactant also increases. So we will get a straight line with a positive slope. So consider the first order reactions. So first order reaction, again substituting here n become 1. So T-half is directly proportional to 1 by concentration of A0 raised to 1 minus 1. 1 minus 1 means it is equal to 0. So A0 raised to 0 means it is equal to 1. So T-half is directly proportional to 1. That means T-half is independent upon the concentrations of the initial concentration of the reactant. So when we plot a graph for a first order reactions between T-half on the y-axis and A0, that is initial concentrations of the reactant on the x-axis, here T-half will be independent upon the initial concentration of the reactant. So we will get a graph like this. So for a first order reactions, it will be independent upon the initial concentration of the reactant. So plot will be like this, and for a zero order reactions, T-half is directly proportional to the concentrations of the reactant. So when we plot a graph, we will get a straight line with a positive slope. And general equations, that is connecting the T-half and the initial concentrations of the reactant for n order is T-half is directly proportional to 1 by A0 raised to n minus 1. So for a second order reaction, again when we are plotting a graph between T-half and initial concentration, again for a second order reactions, the general equation is T-half is directly proportional to 1 by A0 raised to n minus 1. Here for a second order reaction, n become 2. So T-half is directly proportional to 1 by A0 raised to 2 minus 1. 2 minus 1 become 1. So it becomes T-half is directly proportional to 1 by A0. So again when we are plotting a graph between T-half on the y-axis and x-axis, 1 by A0 means we will get a straight line with a positive slope. But when we are plotting a graph between T-half and concentration, simple constant on the x-axis, that is when T-half increases, definitely initial concentration decreases. That means it is inversely proportional. So when T-half and concentration, simple concentration of reactant we are plotting, we will get a negative, that is slope will be reverse and with a negative slope. So here we are plotting a graph between T-half and the 1 by A0. So we are getting a graph with a positive slope. Next we can determine how to determine the order of the reactions. So there are 4 methods to determine the order of the reaction. First is the initial rate method. Second one is the half-life method. Third is the integrated rate equation method. And fourth one is the Postword isolation method. So let us discuss the first method, that is initial rate method. So for that, consider a general reaction, that is Na plus Nb plus Nc giving product. And we can write the rate equation as R is equal to K into concentration of A raised to alpha into concentration of B raised to beta and concentration of C raised to gamma. Suppose this is the rate equation obtained experimentally. So to find the order of the reactions, by initial rate method, we have to first keep the concentration of B and concentration of C as constant. Then we have to change the concentration of A, because in this rate equation, the rate is depending upon the concentration of A, concentration of B and concentration of C. So determine the order of the reactions, we have to keep the concentration of B and concentration of C constant, and we have to change the concentration of A. So if concentration of A changing means the rate also changes at each concentration change of A. So we can write, that is, first if we are taking the concentration of A is concentration of A1, then R1 becomes K into concentration of A1 raised to alpha, concentration of B raised to beta, concentration of C raised to gamma. Again, if you are changing the concentration of A to A2, then again rate changes, that is R2 is equal to K into concentration of A2 raised to alpha, concentration of B raised to beta, concentration of C raised to gamma. So when we divide these two equations, that is 1 by 2 equation, so R1 by R2 is equal to, here B and C are kept constant. So there will be no change in the B and C concentration. Again rate constant is same, so the R1 by R2 is equal to A1 by A2 concentration raised to alpha. So applying logarithm on both sides, that is log R1 by R2 is equal to log of A1 by A2 raised to alpha. So here log, it is in the form of log A raised to B. Log A raised to B means B log A. So here alpha will come front. So log R1 by R2 is equal to alpha into log of A1 by A2. So alpha is equal to, we can find the order of the reaction, that is alpha is equal to log of R1 by R2 divided by log of A1 by A2. Suppose if we want to find the order of B with respect to B, that is beta, again A and C can be kept constant and we have to change the concentration of B. And similarly we can find the beta also. Similarly, if we want to find the gamma means, we can keep concentration of A and concentration of B as constant, and C concentration we can change and we can find the gamma of the reaction. In this way, that is initial rate method, the order of the reaction was found out. So coming to the second method to determine the order of the reactions, that is the integrated rate equation method. Actually, this is a trial and error method. So we have already discussed the integrated rate equations for a zero order reactions, first order reactions and second order reactions. And we have found that for a zero order reactions, the rate equation is K is equal to concentration of A0 minus A divided by T. Again, for a first order reaction, we found that the rate equation is K is equal to 2.303 divided by T into log of A0 by A. Again, for second order, we found that K is equal to 1 by T into concentration of 1 by A minus 1 by A0. So, whatever we are getting the experimental result, we are substituting in these expressions of different order. Then, the one which gives the constant value of the K, that is rate constant, which design the order of that reactions. That is the integrated rate equation method. So, integrated rate equation method is a trial and error method. After getting the experimental result, we are substituting in these expressions to find the order. Then, the one which gives the constant value give the order of the reactions. So, coming to the third method to determine the order of the reactions, that is half-life method. We know that half-life, that is T half, is related to initial concentration of the reactant, as that is T half is directly proportional to 1 by A0 raised to n minus 1. So this is the general relation for the nth order of the reactions. So if T half for two different values of A0 are known, then we can substitute it in this equation and then we can find out the order of the reactions. So this is the way in which order of the reactions are determined by half-life method. So coming to the fourth method to determine the order of the reactions, that is Postword isolation method. So consider the reaction, that is N1A plus N2B plus N3C gives the product. And suppose we are getting the rate law as R is equal to K into concentration of A raised to alpha, concentration of B raised to beta and concentration of C raised to gamma. So in the Postword isolation method, we are taking all except one in excess one by one. Then the order with respect to that reactant can be determined. That means Here, first B concentration and C concentration are keeping in excess. Then the rate won't depend upon the concentration of B and concentration of C. Rate will depend only on the concentration of A. So order with respect to that A we can find out. And then again in the next method we can keep the concentration of A and C in excess. Then the B is keeping unchanged. So rate will depend only on the B, and if the concentration of the reactant are keeping in excess means rate do not depend upon that reactant. So if A and C concentration are keeping in excess means the rate will not depend upon the concentration of A and concentration of the C. So rate will depend only on the concentration of the B. So order with respect to B we can find out. Similarly, if we are keeping the concentration of A and B excess and that C unchanged means rate with respect to that is order with respect to C we can find out, because rate won't depend upon the concentration of the A and B, because A and B concentration are keeping in excess. So in this way we can find out the order of the reactions. So this is the way in which Postword isolation method order can be calculated. So that is all in this session. Hope you like this session. Stay tuned for the next session. Till then, bye.